All right, we are back looking at Briggs section 3.2. So last section, towards the end, we introduced the derivative. So we're going to expand on that a little bit more. Okay, so starting off, we've got our definition of the derivative. So the derivative of f, where f is just some function, okay, is given by this limit, and it's the limit of our difference quotient. And this will be what we call our limit definition of our derivative. Okay. That's t. All right. And so our derivative is given by this limit as long as the limit exists and x is in our domain of f, our function. Okay, and then if f prime of x exists, then f is differentiable at x. Okay, and if f is differentiable at every point on an interval, we say f is differentiable on I. So in that case, if we had some interval, let's say from 2 to 4, okay, if f was differentiable at every point between 2 and 4, then I would say f was differentiable on 2 to 4. And then we've got just some different ways we can note the derivative. So you might see f prime of x. Okay, we might also see d over dx, or derivative with respect to x. Similarly, you might see capital D with a lower script x, or y prime. Remember, f of x is equal to y. It's just function notation. Okay, so it's the same thing. All four notations mean the same thing, just a different way of writing it. Then we've also got notations for the derivative of f evaluated today. So just like we can have a function and then we can evaluate that function at a point, our derivative's a function, okay? And then we evaluate our derivative at a point. Okay, so we could have f prime of a, y prime of a, the derivative of f with respect to x, evaluated. So this little line here means evaluated, and then the x equals a at the bottom of the line tells us what x equals to. Okay, similarly, we can have dy dx, okay, with the same line that means evaluating, and we're still evaluating at a. Okay. Now, so an example might be is if they say to use the limit definition. Okay, if they say use the limit definition, they want you to use our limit definition that we gave up here. All right, so if we're using the limit definition of our derivative, to find our derivative of our function f of x, so we've got f of x is here. Okay, and so we're looking for f prime of x using our limit definition. So the limit as h approaches 0 of f of x plus h minus f of x divided by h. All right. And then what was our function? There it is. All right, so we can take and plug our function in just like when we were evaluating difference quotients or our rates of change. All right, and so we've got 5x plus h squared minus 6x plus h plus 1 minus our original function all divided by h. All right, and then we can expand everything out and simplify. Again, this is really similar to the last several sections that we've done. Okay, something to be careful of when we do go to simplify, make sure that negative gets distributed to each of the terms in the second function, or your original function. Okay, and then again, still all divided by x. And then we can cancel our terms. And everything in the numerator that doesn't have an x in it should cancel. And we are left with 10xh plus 5h squared minus 6h divided by h, which is equal to the limit of h approaches 0, 10x plus 5h minus 6. Okay, because we have an h in each one of these terms, so we can factor it out and then cancel with the denominator. All right, and now we can evaluate our limits. We can plug 0 in, and we end up with this 5h going to 0. So we're left with 10x minus 6, which is our derivative. So our derivative for f prime of x, okay, is 10x minus 6. All right, we can also we can use the limit definition and find the derivative of our function f of w. Okay, so we're looking for f prime of w in this case. It's whatever variable is in the function. So the limit is h approaches 0 of f of w plus h minus f of w divided by h. And that is equal to the limit as h approaches 0 of square root of 4 times w plus h minus 3 minus square root of 4w minus 3 all divided by h. Alright, and we can rationalize that, so we'll multiply by the conjugate, which in this case is square root of 4w plus h minus 3 plus square root of 4w minus 3 over itself. Alright, so we multiply by the conjugate, and we get the limit as h approaches 0 of 4 times w plus h minus 3 minus 4w minus 3 divided by h times our conjugate. Okay, and then we make sure we distribute this negative to both terms. We end up with the limit as h approaches 0 of 4w plus 4h minus 3 minus 4w plus 3 divided by h times our conjugate. The conjugate really just kind of tags along. We can cancel our terms in the numerator, and we get it down to a 4h divided by h times our conjugate. Okay, so we can cancel the h's and get the limit as h approaches 0 of 4 over our conjugate. Which we can then evaluate. So we'll plug 0 in to our function. So we get 4 divided by square root of 4w minus 3 plus square root of 4w minus 3, which simplifies to 2 divided by square root of 4w minus 3. Okay, because if we add these two together, we get 2 times the square root of 4w minus 3, and then 2's cancel. Okay, because 4 divided by 2 is 2, and that's what we're left with. Okay, and so then that's our derivative. Okay, now this problem asks us to do one more step. It asked us to find the tangent line at that point. Okay, so we've got our derivative, and then last section we looked at finding tangent lines. Okay, and remember our tangent line was y minus f of a equal to f prime of a x minus a. Okay, and so we've got our derivative, and so we can evaluate that at a, which in this case is 3. So we get y minus f of 3 is equal to f prime of 3 times x minus 3. Okay, and then we can plug in our values for f of 3 and f prime of 3. All right, and so we can find those down here real quick. So f of 3 is going to be equal to 3. I'll work that one out. So we have the square root of 4 times 3 minus 3, which simplifies down to 3. Okay. And then we can take and find f prime of 3. F prime of 3 is going to be 2 divided by the square root of 4 times 3 minus 3. So we end up with 2 divided by 3. All right, and we can plug those in up here, so we end up with y minus, we said that was 3, is equal to 2/3 times x minus 3, and then we just solve for our line like we did in the last section, and we get y equals 2/3 x plus 1. Okay, and so there's our tangent line. Alright, so that example combined a little bit of the new stuff and a little bit of what we were doing last section. Alright, we can also find so this problem, okay, notice the notation is using a different one than the prime, but totally cool. We're still just doing the derivative of the function. Okay, and so we'll do it the same way. So we're finding derivative with respect to x, which all that means is x is our variable for this point of this function. All right, and so I know there's no numbers in there, but we do it the exact same way. Limit as h approaches 0 of square root of a times x plus h plus b minus square root of ax plus b divided by h. All right, multiply by our conjugate. Square root of ax plus h plus b plus square root of ax plus b. Let's do this real quick just so it makes it a little easier. Alright, so we multiply by our conjugate and we end up with limit as h approaches 0 of ax plus h plus b minus ax plus b divided by h times our conjugate. Alright, and that simplifies. That simplifies to be the limit as h approaches 0 of ah divided by h, there should be parentheses there, around our conjugate. Alright, our h's cancel and we're left with the limit as h approaches 0 of a divided by our conjugate. Then we can evaluate the limit, plug 0 in for our h. So we are left with a over 2 times the square root of ax plus b. Okay, and that is our derivative of square root of ax plus b. Okay. Now, we can also take the derivative. So, because we did this in a general form, then we know that our derivative for whatever numbers are in here is going to be in this form. Okay, so if we do the derivative of square root of 5x plus 9, okay, notice it's in the same form as we did up here with the ax plus b. So we know then our derivative of that is just going to be equal to 5 divided by 2 times the square root of 5x plus 9. Okay. Because we did that general form up there. Now, if the problem asked specifically and says use the limit definition, then you have to use the limit definition. But anytime you do one for a general form like that, then it applies for any case of a and b, or whatever variables you have. Okay, and so now we just have left to find our f prime of -1. So we would plug -1 into this. Okay, and I can interchange these notations because they're the same thing. Okay, so I'll plug -1 in for my derivative. Alright, and so we get 5 divided by 2 times the square root of -5 plus 9 is 4, so 5/4. Okay. Alright, so there's some examples of finding your derivative as a function and then evaluating that derivative of a function at a point. Okay. If we look at a graph of our function and the graph of derivative, we can notice some relationships. And so here's a table with some of the common ones. If our original function is increasing, our derivative graph at that point, the function is going to be positive. If the function is decreasing, derivative graph will be negative. If there's a smooth min or max, so this means something like a curve, not a sharp point, then that means we'll have a root or a 0 or an x-intercept at that point. Okay, all those words are synonyms, so whichever one you want to use. If our function is a constant, which just means it goes in a straight line like this, it's not increasing or decreasing, then that means our derivative graph will be 0 on that interval. And if our function is linear, derivative is going to be a constant function. If it's a quadratic, our derivative is going to be linear. And if there's a discontinuity in our function itself, so if there's a hole or something, there's also going to be a discontinuity at that same point in our derivative graph. Okay, so these are some things you should know, these relationships, I guess is the best way to call them. Because you might get asked a question like, here is our original graph. Now draw the slope graph or derivative graph, whichever word you want to use. Okay, and so we can do that. I recommend using these 4 steps. We can try that now. So our first step is going to be to find where the slope is 0 on our original graph. So that would be where there is a horizontal tangent line, or where there is a min or max, okay, that is smooth. No sharp points. Sharp points mean something different. Okay, but so we know at that point our derivative graph is going to have an x-intercept or 0. So my derivative graph at this point is going to intersect the y-axis. So our x values stay the same. It's the y-axis values that change. All right, so then our next step is going to be to note intervals where f of x is increasing or decreasing. So we know that from, I think that's a -5. -5 to we will call that 1.5. I should have labeled that better. Your graphs that you're given should be labeled much better. So we'll have a -1 here, and it'll be just past this 1. Okay, so we know that from on this function, or on this interval, our function is increasing. Okay, so that means over here it'll be positive. So it'll be somewhere above the x-axis. Okay, we also know that, okay, so we can mark that interval. We also know that from whatever that point is a little past -1 to 0, our function is decreasing. Okay, so that piece of our slope graph will be below the x-axis. Okay, we can do the same. And that looks to be a little before 2. Okay, and then we've got from that point to 5. Our function's decreasing, so it'll be negative. All right, so we've got all of our intervals laid out. Now, so identify discontinuities. So discontinuities are anywhere where the function's not continuous. So vertical asymptotes, places where there's a a vertical tangent line, sorry, and sharp points or holes or gaps somewhere. So in this graph we have two, I'm going to erase this so you can see it. We've got two sharp points. So at those points, I'm going to have some sort of discontinuity on my graph. Okay. And then, so the last step, we've got the min and max of our derivative graph occurs where f of x is the steepest. Okay. And on this one, it's kind of hard to tell. Well, yeah, on this one, it's because they're linear, they're kind of all equally steep, but we can see in our quadratic, it's a little steeper in here. So steepest just means how, so if we were to have two lines like this one and this one, okay, this one would be more steep. All right. Which that one's not a big deal, but we're steepest, I think, here and here, somewhere thereabouts. Okay. So we know that there'll be a min and max of our function there. All right, so now we've got all of that, we can start to fill in our graph. We'll start with the min and max. Okay. So we know on our interval here, my function is decreasing, so it'll be below the x-axis. So that means this point will be a min. Mins will be below the x-axis. Okay, and we also know we have to intersect here. All right, so I can draw in this chunk. So we'll intersect there. That is a terrible line. Okay, so we've got our discontinuity here, and we've got our, this will be our minimum, so none of the other x values will come below this point. Or none of the other y values, sorry. All right, and then we've got a maximum, so over here this chunk is increasing, so that means this will be a maximum value. Okay. So we can have our maximum somewhere about here, thereabouts. And we know we'll also have a discontinuity somewhere over here. Okay, so I can fill in this section of my graph. All right, and then beyond that is just filling in the rest of it to match. We're increasing on this first interval, and we know we'll have a discontinuity here, so we're increasing, so we'll be up here somewhere. So we can say, well, because it's, shoot, I did that wrong. Sorry, guys, I wasn't paying attention to what I was doing. All right, because this chunk and this chunk are pieces of a quadratic. Okay, remember I said up here, quadratics are going to be linear. So when we do those sections on the graph, those are going to be lines. We'll still have our min and max, and that'll be the same. They just have to be lines instead of the swoopy lines that I made. Okay. So we'll have a line there, their maximum. And that discontinuity. And then on this interval, that one was green. We're decreasing, so we're below, and we'll have a minimum. Okay. All right, and so then on our other two pieces, okay, over here, this one is linear, so it would be a constant function with the discontinuity, constant function above the x-axis, discontinuity there. All right, and then this last chunk, okay, decreasing, so we're below the x-axis, and it's linear, so this one will be constant with the discontinuity. All right. Okay. I would start, when you go to do these, okay, figure out where your zeros are. Then your discontinuities and your intervals with increasing and decreasing. Those are listed as 2 steps, but you can kind of combine them because those are the 2 things that'll break this x-axis up, so then you can figure out where it goes where. Okay. All right. Now, a function is, the next thing we have to look at is when is a function not differentiable? All right, so a function's not differentiable if at least one of these conditions hold. Okay? You don't have to, more than one can hold, but it has to be at least one of them. So if a function is not continuous at a point, then the function is not differentiable at that same point. It could be differentiable at another point, but it won't be at that point. So for example, if we had something like this, okay, it's got to jump, some holes, it's not continuous. All right. The second would be if the f has a corner at a point. Okay, so if we've got a sharp point, okay, remember I said corners. Or f has a vertical tangent. Okay. Now, f having a vertical tangent would be something like this. Okay. And if that's the case, then at that point, the function is not differentiable there. Okay. And this one was vertical tangent. All right. And then we've got 2 theorems. So f is differentiable at a, or if f is differentiable at a, then f is continuous at a. So we've got the differentiable implies continuous. Okay. Now, differentiable implies continuous, but the opposite's not true. So continuous does not imply differentiable. I can't look at a function and say, oh, it's continuous, so therefore it's differentiable. Not true. So we've got differentiable implies continuous, and then we've got another function. Okay, if f is not continuous at a, then f is not differentiable at a. So not continuous implies not differentiable. All right. So differentiable implies continuous, and not continuous implies not differentiable. Okay. But not differentiable doesn't imply not continuous, and continuous does not imply differentiable. Okay? So both of those are one-way statements. All right? Then the last thing I think we do in this section is called the normal line. All right, so we've talked about tangent lines. Now the normal line at a point is the line that's perpendicular to the tangent line that crosses that point. Okay, so if I've got some function, la-di-da, there's a function, and I've got a tangent line at a point A. Okay, the normal line is the one that's perpendicular to that, so it's got that right angle. Okay, and that's our normal line. And there's our tangent. Okay, that's what our normal line is. So we can see an example that'll say something like, find the tangent line and the normal line of a function. Okay, so to find we gotta find our tangent line first. So to do that, we first need to find our derivative. Okay, so we'll find h prime of x. Alright, so we'll use our limit definition. So the limit as h approaches 0 of h x plus h minus h of x divided by h. Now, most of the time your functions probably won't be named h, and if they are, just in this step, be careful not to confuse this h with the h of your function. Okay, but that confusion should go away as soon as you plug in your function in the next step. Alright, so we have the limit as h approaches 0 of 2 divided by the square root of x plus h squared plus x plus h minus 2. Alright, minus 2 divided by square root of x squared plus x plus 2, all divided by h. Alright, so that we can simplify. So we can rewrite it. We can have the limit as h approaches 0. I'm going to rewrite this so that it's 1 over h times my numerator. Okay. And then, so it's the same thing, just rewrote it. And so then we can find where we can multiply by our conjugate. Well, let's find a common denominator first, and then we'll do the conjugate. We'll do that in 2 steps. Okay, so if we do the limit as h approaches 0 of 1 over h times, we'll find a common denominator, and we get the square root of x squared plus x minus 2 times the square root of x plus h squared plus x plus h minus 2. And all that divided by square root of x squared plus x minus h times the square root of x plus h squared plus x plus h minus 2. Okay, so now we can multiply by our conjugate, which is square root of x squared plus x minus 2 plus the square root of x plus h squared plus x plus h minus 2. Copy that real quick. Alright, so we multiply by our conjugate, and we get the limit of h approaches, or the limit as h approaches 0 of 1 over h of 2 times x squared plus x minus 2 minus 2 times x plus h squared plus x plus h minus 2. Or is that a plus 2? That's a minus 2. Alright, just checking. Alright, all that over square root of x squared plus x minus 2 times square root of x plus h squared plus x plus h minus 2 times our conjugate. Alright. Okay, now we can simplify some, and I'm going to copy our denominator just because it's so long. Alright, our numerator simplify, and we get the limit as h approaches 0 of 1 over h times negative 4xh minus 2h squared minus 2h divided by our very nice long denominator. Okay. Now I've got an h in each of my terms up here. They'll cancel with our h down here. Limit as h approaches 0, and I get negative 4x minus 2h minus 2 divided by our nice very long denominator. Okay, now I can evaluate my function, so I'll plug 0 in for my h's, and I get negative 4x minus 2 divided by x squared plus x minus 2 times times 2 times the square root of x squared plus x minus 2, okay, which is equal to negative 2x minus 1 divided by x squared plus x minus 2 to the 3/2. Okay, so if we simplify these, okay, this divided by 2 simplifies, and then our two fractions, or two radicals, I guess. Okay, and then this is our derivative. So h prime of x. Okay, now that we have that, do I have enough room? Yeah. Okay, so now we can find the tangent line. Same way we were doing before. So in this case, it'll be y minus f of 4, or sorry, h of 4. Equal to h prime of 4 times x minus 4. Okay, and so we can come over to the side here and do h of 4 will just be 4 plugged into our original function, which that simplifies. Okay, and then we can plug it into the derivative. Okay, so we can use those values down here. So y minus 2 over 3 square root of 2 is equal to minus 1 over 6 square root of 2 times x minus 4. Okay, solve for the equation of that line. Sorry. That x plus alright, and then that simplifies down, and we get our line is negative 1 over 6 square root of 2x plus 4 over 3 square root of 2. Okay, so there's our tangent line. So our last step is to find our normal line. So we're looking for the line that's perpendicular to our tangent line. Okay, so that means, okay, it'll just have the reciprocal slope. So what we do there, so our tangent line, so for our normal line, take your derivative, find the negative reciprocal of it. So the normal line will be y minus 2 over 3 root 2, that's the same, equal to 6 square root 2. So the 6 square root 2 is the negative reciprocal of this. Your derivative evaluated at that point, 4. Okay, so take whatever your function is evaluated at that point, or your derivative is evaluated at that point, negate it, so change the sign, and flip the fraction. And that's your slope for your normal line. Okay, the rest of that equation is the same though. And that gives us our equation for our normal line. Alrighty. Now, most of your problems won't be this complicated. That was just a lot of algebra. But it allowed you to see how the process worked. Okay, and cover any bases I think you might see. All right, I look forward to hearing your questions in our discussion board and Zoom office hours. All right,